Okay, try again. We are immediately in an inception mode today. It is April 19th, Monday. This is CS-030. It is April 19th, Monday. This is CS-030. Looks like we're broadcasting okay. Monday. This is CS-030. Looks like we're broadcasting okay. Monday. This is CS-030. Looks like we're broadcasting okay. Let's shift off inception. Let's shift off inception. Let's shift off inception. Let's shift off inception. Okay, hopefully everything is still broadcasting for you. Good morning. This is actually class 37. Let's update that. All right, let's run through our checklist. Quiet down our music for a second. All right, and run through our checklist to make sure we're all set up for the day. I've gone through my checklist for CS-030. Make sure you've got your VPN on so that we can hear each other if you choose to speak. Find a quiet location away from erupting volcanoes. For example, if you're visiting remotely from Iceland. Turn off notifications on your phone or computer. Make sure I got that going. My notifications on my computer are off. Notifications on my phone are off. I have left my watch at home today, so my wrist is notification free. Put on headphones so we don't get echo when you choose to unmute. Shut down any extra apps or browser tabs that you might have open. I am good to go. I shut down everything before we started. Open Firestorm if you're not already here, and you can join us. It's kind of best experienced in Firestorm if you can. If you're not in Firestorm, then drop your name in live chat. I see Ben Fernberg is there. Make sure you've got Canvas open. If you want to have Eclipse open, I don't think we're going to be using Saros today, but you can have that ready to go. Rebake your avatar. Go under Avatar and Avatar Health and Forced Appearance Update. Make sure we can see full bodies of each other. Set your environment under World and Environment to midday, so it looks like it's the same time for everyone. Set your draw distance to a low enough number that things work all right. Mine's at 288 today. That seems to be okay. Make sure you're in your classroom and check in on the attendance machine. Dodger's back there guarding the attendance machine today. I think maybe he was pushing Ethan around, so sorry about that, Ethan. All right, checking in with who we've got in class today. Let's walk around, see what we've got going on. Morning, Ethan Vaughn, Trent, Sam, Dee Dee, Thomas, and Matthew. Dee Dee, you're sort of invisible woman today, so if you could rebake your avatar, that'd help me. Landon, you're in the busy chair, so good morning. Ethan, good morning. Carson, Faith, you're doing something funky with your head, no fault of your own. Ben, good morning. Morgan, Josh, and Ben, crossing your arms. There you go. Good morning. All right. So on the screen behind me, what I'm going to do here is I'm going to put up a calendar from Canvas. See if I can get that all right. There's our in-game. Setting up my windows and getting our class up, putting the window in place, giving everything a sec to catch up. Restarting my window manager. All right, let's see. The window manager is going to make everything. Yeah, hold on. There we go. Okay, so it is April 19th. It is Monday. On my calendar, it shows that you've got 2 after-class things due today. We'll see if we get there. Also have drone challenge assignment 2 due tonight. That'll be the second of 3 drone challenges. Today you are controlling 5 different drones with one drone controller class. Some of you have begun to broach the idea of using some state that is maintained between successive calls to your drone controller, and you can do that by putting an instance variable in your drone controller class. The way the simulator works is that it only instantiates one copy of your drone controller class. And so any instance variables that you use in your drone controller class remain consistent through multiple calls to your drone. So every time your drone event handler is called, your instance variables will be the value that they were at the last time your event handler was called. And it's the same instance variables regardless of which event handler is called, and so that's a place to just store information between successive calls to your drone handler. We are ending our chapter 14 discussion on sorting and searching, and hopefully we'll be able to talk about big O notation today. Last chapter will be chapter 17, which we will tackle about tree algorithms. Any questions or comments before we dive into the work on sorting and searching? Any questions or comments? Double broadcasting for a sec. Okay, hearing none, let's go ahead and get started. What I want to do is I want to go back to our selection sort algorithm that we were looking at before. And I just want to remind you how selection sort worked. We used this example of, or I tried to demonstrate it using an example of the Santas. Let me see if I can pull that slide up. There we go. So just as a way of thinking through the algorithm, we wanted to order a bunch of Santas that were auditioning for a mall job of scaring little kids to death by having them sit on his lap and have them tell them everything they dream for Christmas. Mall Santas, maybe we would like to audition them in order by height, perhaps, and so we need to put them in order of height. This is a little bit contrived example, but it helps us to connect what we're learning in code with the physical world. So if our Santas that are waiting outside in line are like the elements in our array that we would like to sort, the way selection sort works is it goes through all the elements in line, all the Santas in line, and picks the shortest one next, if we're going from shortest to tallest, and moves that into the audition area and puts it at the, moves each Santa in order of height, putting it inside the audition studio in the order in which they were received. And so everyone inside the studio is in the correct order, and everyone outside of the studio is in some unknown order. And each step of the algorithm entails going through the remaining Santas, picking the lowest Santa out, shortest Santa out, and putting them inside the studio. And to sort of further demonstrate that with a less contrived example, what I would like to do is show you a visualization of this working in a web application. So let me see if I can pull that up now. All right, so what we're looking at here, and let me see if I can make sure we got selection sort. What we're looking at here, it's paused, and we are looking at an array. This is more straightforward data. The vertical bars represent the value in each position in the array. This array, I believe, has 100 elements in it. There's a number underneath each bar, which describes the height of the bar in question. I'll zoom in on it in a second, unless I can just do that right away. Let's see if I can do that easily. Can't do that easily. Okay. Oh, width 100. Let's try that again. All right. Well, despite the promise of being able to rechange the canvas size, that didn't seem to do much. Okay. So each one of these bars has a height, and what we're trying to do is sort it by shortest to highest, or from lowest number to highest number. And so the numbers underneath the bars are equivalent to the height. And what this is going to demonstrate is the process of going through and doing selection sort to try and give you a visual understanding of what's happening. And so you'll see that just like the Santas, each one of these blue bars is outside the studio, and we're going to go through and we're going to select the shortest one and move them over to the left-hand side of the array. The portion of our array which is unexamined will grow smaller and smaller, and the portion of our array which is examined will grow larger and larger as we move one bar from the right side of our array to the left side. The right side and the left side, what exactly is the right side and what exactly is the left side is going to vary over the course of this algorithm as we sort more and more elements, and the boundary between sorted and unsorted moves from nothing to everything. So let me go ahead and play this and see if I can zoom in so you can see it a little bit better. We're just going to let it play out to get a sense, kind of a gut feel of what's happening. What we're seeing here is we're seeing the algorithm go through and try and select the lowest element. The red element is the lowest so far, and we continue selecting for the lowest. 4, the lowest element, is moved to the left, and now 22 becomes the first element to the right in the unsorted area. We go through and we search for the next shortest bar, next lowest element, and 4 is the one we found so far in this common algorithm of calculating the minimum or finding the minimum. We need to keep track of both the value of the minimum and the index of the minimum, because after we're done searching the unsorted right half, we need to swap it in to the lowest position in the sorted, or the highest element in the sorted half, sorted portion, and the lowest element in the unsorted portion. So notice that 5 and the 50 are going to swap, 40 are going to swap. There they go. Now we're going to find that the 6th is the lowest element in the unsorted. Oh no, sorry, 6 and the 32 are going to end up swapping when we're done doing the search of the unsorted portion here. Okay, 6 and 32 swap, and we begin the search for the lowest element starting at index 4, where the 32 is. 20 is the lowest, now 18 is the lowest, now 15 is the lowest, and eventually 12 will be the lowest and swap with 32. So something to notice here is that each time we would like to put a new element into the sorted portion of our array, we have to search the entire upper portion of our array. And so if our array is 100 elements long, that means we have to search about 100 elements at the beginning, and then we sort one element at the end. And so on average, we have to sort 50. We have to look through 50 elements. That's what it ends up averaging, because in the beginning we have to search through 100 elements, or 99, and at the end we have to search through 2 elements, so 2 ends up being about an average of 50. We get the number 50 because we have a total of 100 elements in our array, and 50 is half of that. So if more generally we had 1,000 elements in our array, the number of things we would have to search through each time in order to move something from right to left is going to be 500. If we had 2,000 elements in our array, the average would be 1,000. If we had 1,000,000 elements in our array, the average would be 500,000. So the general formula for how many things we have to search through in order to find the lowest element is n over 2, where n is the length of our array. So we have to search n over 2 elements in order to move one element to the left side. So every one of these searches is n over 2 long, and it enables us to move one element to the left side. We have more than one element we need to move to the left side. In fact, in our array of 100 elements, we need to move 100 elements to the left side. So we have to do a search of n over 2 elements 100 times. 100 searches of n over 2 elements. Why 100? Because our array is 100 long. So we have to do n searches of n over 2 length in order to finish our array sort. N times n over 2 ends up being n squared over 2. And that n squared term in our array is why we saw a parabola shape when we measured the profiling behavior of the selection sort. So let me see if I can speed this up a little bit so that we can watch it finish. Sorry, I'm gonna get you motion sick here for a second while I speed up the array. All right, and then that's gonna allow us to go through each time. We'll just let it play out. I feel like watching this, getting in your Zen mode and trying to understand what's happening, For me, I'm a real visual learner, so having demonstrations like this really helps me to understand what the algorithm is doing. Once I have a good visual sense of what's happening in an algorithm, it's easy enough for me to duplicate that in the code because I kind of have in my mind's eye a picture of what I'm doing. As the portion of the array that we're searching over gets smaller, you can see that the algorithm speeds up. And as we get closer and closer to the end, it takes less and less time in order to complete the fill of our array. The left-hand side is completely ordered. The right-hand side is unknown, presumed unordered. And we slowly complete the algorithm. Or I guess with increasing speed, we complete the algorithm. All right, very satisfying. I don't quite understand the meme of try not to be satisfied, but I think it applies here, whatever that YouTube meme is. Okay, so great. So that's an algorithm describing selection sort. Let's see if we can mathematically get to a point where we understand why we're getting that n squared behavior. Well, so let's see. Let's look at the code again one more time. Okay. So here again is the code that we were working with, this sort algorithm here. The loop on line 13 was going from position 0 to the length minus 1. So this outer loop is searching for the minimum element. Or sorry, the outer loop is filling the first element with the lowest number. The loop 15, the loop in line 15 is coming from a method call to minimum position. Minimum position runs the interior loop. Minimum position is the loop that gets smaller and smaller and smaller as we find the minimum of the remaining elements. So minimum position takes n over 2 if we average it over all the values of 13, line 13. So we have to, line 13 is where we go through each element of our array and we put the smallest element into position 0, then 1, then 2, then 3, and then 15 is where we search the Santas that haven't come into the room yet to find the smallest one to put in the lineup. All right, so our outer loop is going from 0 to a dot length, or n minus 1, and then our inner loop is going through the remaining elements, so on average n over 2. So let's zoom out and go to that analysis. So in an array of size n, if we want to count how many times a particular array element is visited, we can use the following analysis. We know that to find the smallest element, we're going to visit n elements. So we're going to have to touch n different elements to look at them. And then once we've identified which is the smallest, we're going to have to look at 2 additional elements in order to swap them. So we've identified the minimum from the right-hand side, and now we're going to have to look at that minimum, and we're going to have to look at the lowest of the unsorted in order to do the swap behavior. So finding the smallest entails visiting n plus 2 visits. To find the next smallest, the next time through the loop, we have to visit n minus 1 elements, and then do 2 visits to do the swap. The next time we're going to do n minus 2 elements plus 2 visits, then n minus 3, then n minus 4, until eventually we get to 1 element, or 0 or 2 elements and 2 visits for the swap. So that last bullet point, the last term is 2 elements visited, that when our n gets small enough, to find the smallest, and then 2 visits for the swap. So that's the sequence of finding all the minimum elements. And if we do all of those, we'll have sorted our array. That's sort of combining both of the loops together. All right, so if we add these up, we can see that we start over here in the upper left. Can you see my mouse? Can someone validate whether or not you can see my mouse right now? Mouse? Anyone? Mouse? Great. Right. Oh, good. Thomas, appreciate that. Okay, I appreciate the callback, Ben and Landon, and then I also appreciate the acknowledgement that it's satisfying to watch the sort. Okay, so our first chunk here, n plus 2, that's how many visits it took to find the very first minimum element and then swap it into position, find the first shortest Santa. The next chunk, we had n minus 1 Santas to search over and 2 to swap. And then n minus 2 and 2 to swap. Until we get to the end of the array, we are only looking at the 2 remaining elements, the 2 Santas that are sitting outside in the cold, and then we only have to swap the 2 that are remaining. And then we can move them out. So now we can rearrange this formula at the top And we can just move all the components that have n to the left-hand side. So we have n plus n minus 1 plus n minus 2 all the way down to 2. So that becomes this first chunk here. And then how many 2's are we adding up? Well, we're adding up n minus 1 copies of the 2. So that's where that n minus 1 comes from. There's 2, 2, 2, 2, and we end up doing it n minus 1 times because we don't need to do it the last time because our last Santa must be the shortest out in the cold. This particular sum right here, n plus n minus 1 all the way down to 2, we can rewrite as this, this formula, this expands into this particular series. So we can write this chunk over here as n times n plus 1 over 2 minus 1, that's included in there as well. And then our second piece, n minus 1 times 2. Now, if we take all of these terms, we multiply through and we collect the various components here. Here's like our n squared over 2 plus n over 2 minus 1 plus 2n minus 2. We get all those together, our minus 1 and our minus 2 becomes minus 3. We have 5 halves n end up right here. That's because we have n distributed over n plus 1 and n over 2. Plus we have 2 n's over here, so we end up having 5 halves n, and then we end up having 1 half n squared. So if we have an array of size 100, we can use this formula to indicate how many elements in our array we're going to end up visiting. So it's going to be 1 half 100 squared plus 5 halves 100 minus 3. That's how many times we're going to have to touch our array or look at elements in our array. That corresponds to time. Every time we have to look at an array, it's going to take a little bit more time. So when we looked at our graph of profiling our selection sort, we saw evidence that something about this is mirrored in our profiling. So let me go back to our profile. Remember this is a formula, 1 half n squared plus 5 halves n minus 3. This is dominated by an n squared term, which is a parabola. And let's see if I can get back there quickly. There we go. So this graph, remember, represents how much time it takes to run the selection sort algorithm as the size of our array varies. This is something that you were able to do, or hopefully were able to do after class. And this graph roughly has an n squared shape to it. It certainly is growing faster than linear, so it's got to have some value of n that's greater than n. And we can see that because we're able to see it in the formula here. So now, in computer science, what we like to do is we like to talk about things in terms of really large numbers. And when you have really large numbers, what dominates here, the cost of this algorithm that dominates, is this largest term at the beginning. Because when n starts getting bigger, the relative value of n squared just swamps n and completely swamps 3. And so pretty soon, as the numbers get large, the value of n is trivial compared to the value of n squared. I mean, just think of like, even if you were to just start with 10, 100 is much larger than 10. And if you go to 100, so that would be 10,000 is much larger than 100. And this term is just growing so much faster, it's the primary thing that we care about. So we do this kind of analysis in computer science called big O notation, where we do some kind of, an evaluation of how much time the algorithm takes, as indicated by the formulas at the top. We resolve it into an expression as shown at the one here with the 1 half n squared expression. And then we just focus on what the largest term is that depends on the size. So n squared here. We're not concerned about this constant, 1 half, because we're just concerned with comparing different algorithms. And when we compare them, the constants are kind of a wash. So when we ask what is the running time of this algorithm, we use this notation that says it's big O n squared, meaning this algorithm is dominated by an n squared term. As n gets large, we can represent the running time of this algorithm as growing as n squared. We don't like that. We don't like that because we would like an algorithm, or we would like an input that's twice as long to take, not n squared as much time. That's sort of a problem. So just to reiterate the bullets here, when n is large, 5 halves n minus 3 is small compared to n squared over 2, so we're going to ignore it for sort of just talking about asymptotic behavior. And we're also going to ignore the 1 half because as we compare the running time of two different size arrays, the 1 halves are going to cancel if we just want to say what the relative size is. All right. So the number of visits is of the order n squared. That's the vocabulary we use. We say of the order n squared. And we use big O notation to describe the order of and to describe the growth rate of functions or of algorithms. So we represent that using the big O, looks like a function. And what that means is that multiplying the number of elements in the array by 2 is going to increase the processing time by 4. And we don't like that. Means if we have 1,000 elements, it's not going to take twice as long as 500 elements. It's going to take 4 times as long. So the basic idea of finding the big O notation is to find the fastest growing term in your expression and ignore constant coefficients. All right, so let's shift gears and talk about a slightly different algorithm. Let's talk about merge sort. Merge sort is a little bit different approach to sorting. It's called a divide and conquer algorithm. When we did selection sort, we went through one at a time and tried to pick out the Santas that we were shortest outside. What merge sort does is it separates the Santas into 2 groups and sorts each of them independently. So we're going to cut our array in half. We're going to, here it is, we're going to recursively sort each half. Oh, you thought recursion was going to go away. Nope, we build on it. So merge sort is a really great way in which we can use recursion. And in fact, this is the way in which Java does the sorting. Java uses a divide and conquer algorithm, probably merge sort. It's not required to be merge sort, but it's probably merge sort in order to do collections.sort. Cuts the array in half, recursively sorts each half, so you have 2 small arrays that are independently sorted, and then merges the sorted halves. It is dramatically faster than selection sort. In merge sort, when you sort each half, putting 2 half, if you know that 2 halves of your array are sorted, putting them together is very fast. And so that's kind of where the speed of this comes from. So let's walk through what that kind of looks like. We want to divide the array in half and sort each half. Okay, so what we're going to do is we're going to kind of do our recursion pattern and say, well, let's assume that we are able to divide each subcomponent in half. So the smaller problem, let's assume it works, and it's going to sort each subarray, and then we need to merge them when we're done with our recursive call. So we had some array, we divided it in half, and we made a recursive call, and we assume that it works. We have to have an ending condition, and we have to make our problems get smaller. That's how recursion works. But this is pretty compelling because what we've done to make the problem smaller is we've split our array in half. So that's making our problem smaller. And we can imagine that there's a point at which we only have 1 element in our array, and so that's our ending condition. So that seems pretty straightforward that we could, in theory, do this if we could rebuild our solution on the way back up. So if we assume that we have 2 smaller arrays that have been divided in half and sorted, what we can do is we can keep track of 1 position in each of the smaller arrays, choose which of those elements is smaller, and put them into the new sorted array. All right, so the real trick here is that we don't have to look at each element in the sorted smaller arrays because we know that they're sorted coming back from our recursive call. So if we start with 5, 9, 10, 12, 17 returning from a recursive call, and 1, 8, 11, 20, 32 returning from the second half of our recursive call, we can just keep 1 index, 1 variable like I, pointing to the 5, and 1 index j pointing to the 1, and we can just ask, is 5 or 1 smaller? 1 smaller. So we're going to move 1 into our sorted array, and we're going to move our pointer from our 1 position to our 8. Now in our next iteration through, we ask, is 5 or 8 smaller? Well, 5 is smaller, so we're going to move 5 over into our sorted array, and we're just going to keep track of 9 and 8, the position that 9 and 8 are at. Now we ask, is 8 or 9 smaller? Well, 8 is, so we're going to move 8 over, and we move our pointer forward. Now we ask, is 9 or 11 smaller? 9 is, so we move 9 over and move our pointer forward. Is 10 or 11 smaller? 10 is, move 10 over. Is 12 or 11 smaller? 11 is, so move 11 over. Is 12 or 20 smaller? 12 is, 12 goes over. 17 or 20 smaller? 17 is smaller, so move 17 over. Oh, we don't have anything left in our left-hand side, and we know that our right-hand side is sorted, so we just add our elements one by one from left to right that of the elements that remain. So we had 20, we had 32, we're done. And now we have first made our recursive call, assumed that it worked the way we do in recursion with an inductive, like an inductive proof in math. Now we take those sorted things, we put them together, and we have a sorted array. And now we return this in case we are part of a recursive call and don't realize it. So we return 1, 5, 8, 9, 10, 11, 12, 17, 20, 32. If that's our whole array, it's sorted, great. But if we, in fact, were sorting, doing the work of sorting half an array, then we return that back for our previous call to merge together. It's called merge sort because this operation of putting these two sorted arrays together is merging them together, kind of like shuffling a deck of cards in a way, although when we shuffle a deck of cards, we're not maintaining lowest order. All right. So let's visualize that. Let's look at a visualization of that one. Here's merge sort. Let me pause it for a sec and slow it down so we can see what's happening. And skip back and zoom in. Ooh. And for this one, we need a little bit more space in our visualization because we are going to see things getting cut in half, and then we're going to see them end up in our sorted array at the bottom. All right, so let's see if we can play this. Boop. All right, playing. I swear I hit play. It says it's completed. I guess I need to shuffle it again. Let's see. I am going to randomize the array. Boom. And then I'm going to run merge sort. Sorry for the motion sickness. There we go. All right. All right, so we're splitting everything in half, merging. We split those elements in half. Now we're merging. Let's see if we can see it. Oh, sorry. It's like, is it off screen? All right, hold on. I think when I changed the canvas size, I unwittingly changed the canvas size. All right, sorry. I'm going to zoom out. I'm going to get control here. I'm going to ask this to let me change it. Change the canvas size. I'm going to refresh the page. I'm going to randomize my array. I'm going to do my merge sort. There we go. All right, so we're splitting the array in half and half and half. We're taking the two halves and we're merging them. Here's our second half. Now we're going to merge them together, put them together, do our next bit. Merge those two halves together. That then becomes merged. Pop it up. Now we're going to have to take this chunk of our array and do the recursive sort. There's 4. Now we're going to merge those together. Here's two groups of 2, two groups of 2. Now we're going to have to merge our groups of 4 together. Now we're going to merge our entire lower half of our lower quarter of our array. As the chunks get bigger, you can kind of see a little bit more clearly what's happening. Now we're taking the second quarter of our array and we're recursively sorting it. I hear you typing. I'm a little. If there's something you need, I can't see what you're typing right now, so unmute if you need me to address it right away. All right, so we're doing our second quartile here. And what you're going to see is the lower fourth and the second fourth are going to be sorted, and then we're going to merge those together. All right, here's our second fourth that's getting merged together, and then we're going to merge our entire bottom half. There we go. So we're taking pointers in each of the bottom halves. This is a little bit like the slide deck I just went through. Grabbing one off the bottom, depending on which one's smallest, and then putting it back together. Now, one thing that you shouldn't take from this is you shouldn't think that because the visualization is running faster or slower that the algorithm is running faster or slower. The visualization is running slightly slower because it's moving all these bars up and down to show how the algorithm is working. The algorithm itself, of course, doesn't have to do that. And so the amount of swapping and whatnot is actually, it's much faster. The algorithm is faster. Let me speed up our animation speed so that we can see it wrap up. And probably the most satisfying one is when it does the final halves. Yeah, I'm not sure why it's getting cut off on the bottom. I apologize for that. Here, we're sorting our top quarter. We're going to merge our top half in a moment. All right, merging our top half. And then we're going to take the two halves that were our first recursive call, and we're now going to merge them. And this was our first recursive call, so when we're done, the whole thing's going to be completely sorted. Boom, and it's sorted. Nice. Nicely done, computer. I'm proud of you. All right. All right. So let's take a look at what that kind of looks like when we examine it in a code context. This is some sort function. That's a static method that is embedded into a class. So it doesn't exist on its own. It's in a class. And you can see that sort is taking as input an array of integers. That is an unsorted array of integers. And what we want to do is we want to sort it in place so that what gets returned is sorted. So, like any good recursive algorithm, the first thing that we have to do is set an ending condition so that we don't make infinite recursive calls. Our ending condition in this case is going to be if the length of our array is less than or equal to 1, we're going to return. All right, so if the length of our array is 0, fine, no problem, we're done. If the length of our array is 1, well, that happens to be the definition, kind of a degenerate example of a sorted array, right? If you have an array with one element in it, it is sorted. It cannot be unsorted. And so we can just return that without having to do any work. Okay, now, given that we have an array that has at least 2 elements in it, we're going to split it into a first half and a second half. So when we create a local variable called first, which is an array of integers, it is going to be of size, it's not filled yet, but it's going to be of size a.length divided by 2. So we're going to allocate that much space. Now, here is an instance where we're explicitly using integer division. A.length is an integer, and 2 is an integer literal. And because we have an integer as the numerator and an integer as the denominator, the result is going to be an integer and it's going to be floored. So we're going to throw away the remainder in this case. And that's exactly what we want when we're doing this kind of a recursive algorithm, because we want to split our array cleanly into an upper half and a lower half, but it isn't necessarily the case that we have an even number of elements in our array. So in the case in which we have an odd number of elements in our array, this should have the lower number, so if we have 5, the first array should have 5 divided by 2 is going to be 2. So the first array will have 2, and the second half will have 3. To make sure that we capture all the elements, the way that we calculate the length of our second array is to take the full length and subtract whatever length we ended up with in our first array to make sure that we captured all of the elements. We've commented out the code that simply copies the first part of A into first and the second part of A into second. That's simply 2 loops that would have to have the right starting and ending positions, but it's kind of straightforward. And here's where we make the recursive call. We sort the first piece, we sort the second piece. And so we assume that after we're done sorting, A has been sorted in place. And then we merge them. We merge first and second, and we put the result into the A array. And so this is kind of it. Like, this is sort of amazing that we can represent this really fast sort algorithm in this high-level pseudocode. Sort the first half, sort the second half, merge them, we're done. Now, there are details, of course, in the merge, but the sort is a recursive call. So we're recursively calling this particular element. There's not a lot of code here, and yet it's really, really fast because of the way in which the algorithm is cleverly designed. All right, so let's dig into the details a little bit in the algorithm. So we've got sort and we've got merge here. Let's look more specifically at the sort algorithm. All right, so our sort algorithm, we're doing line 13 as our ending condition, 14 and 15, and we create data structures to hold our smaller arrays. 17 and 21 are the loops where we actually go through and move the data into our smaller half arrays. So 19 copies A into first, and 23 copies the second half into second. Notice the clever use of indices on 23 to find where in A we want to get the data from, but we place it into the beginning of second. We sort first, sort second, merge, and we're done. All right, so what magic happens in our merge? Because that's the only method that isn't described. Our sort method here is completely contained because it's recursively calling itself, but merge is not described. So let's look at how merge works. Zoom out, make you sick, sorry. And see if we can get all of merge in there. All right, so can't quite get all of that in there. I wish I could make that window a little bigger, but I can't make it bigger right now. All right, so we'll scroll down here in a sec. All right, so to merge, we start with our parameters that are coming in. We have a sorted first array and a sorted second array. Those are our parameters, and then we have where we want to place them in A. So in line 38 and 39, we set up two indices as local variables that are going to keep track of what spot we're looking at in the first and second array. And then J is going to be where we're placing things in our destination. So we've got first and second and J. All right, let me zoom out so we can get the rest of the algorithm in place and not make you sick. There we go. All right. So 44 is our while loop that makes sure that we have not run to the end of our array. So what 44 is saying is, as long as the position that we're looking at isn't longer than our first array, and as long as the position that we're looking at isn't longer than our second array. So we want to make sure that we haven't run out of elements to compare. Assuming that we have elements to compare, line 46 is going to check 46 and 51 are checking to see which one is the smallest. If the position we're looking at in the first array is the smaller one, then we're going to move that into the next element in our destination array, AJ. So we're going to take the element from first and move it to AJ. So 49, we bump up the position we're looking at in the first array. And notice that if we do copy the element from the first half, we don't bump up our position in the second array. We keep that the same. You may also notice that since on line 48, we just moved our element in the first array into our destination array, we better also increase J's position, or the next time we come through this loop, we're going to overwrite the element that we just wrote into AJ. Well, we do that down in 56. 56, we increment J, because we know that regardless of which of the if branches we take, 46 or 51, we're going to be writing one element into our destination array. And so rather than duplicating J++, rather than putting J++ in the branch that starts at 47 and the branch that starts at 42, we refactor that J++, bring it out of the two branches because it's code that's in common, and so we don't want to duplicate it. So in 52, we take the opposite case. If second is greater than first, then we're going to move second into the next position of AJ and increment our second indice, but not our first one. And so in this way, we systematically are moving through, selecting the next element in each of our arrays and putting it in our destination array. If first and second, if those two indexes happen to be looking at values that are equal, then we're going to move the value from the second array. Because notice in line 46, if first is less than second, then we're going to move the element from our first array into AJ. But if first and second happen to be equal, it's fine to have two duplicate elements in an array. If first and second happen to be equal, then we end up taking the value from the second array. It doesn't really matter. We could have said, if in line 46, we could have said first, I first, less than or equal to second, or we could leave it as less than. The algorithm will work either way. But it's just when you are coding, you have to pay attention to things like that and think through, well, what happens if we run out of space in our array? That's line 44. What happens if the two elements are equal? That's line 46. All right, so after having gone through our loop in 44, we know that we have exhausted one of our subarrays. But because they're not moving in lockstep, because I first and I second aren't necessarily each being incremented at the same rate, we could exhaust our entire first array before even looking at our second array. And so we know that 44 is checking for that. And so when we leave the loop at 44 and we get down to 61, we know that we've got some tail data to take care of. And so the loop in 61 and 67 is exhausting the rest of that array. So if we get to line 61 and I first is less than first dot length, that means that there's more data to capture in first. And so we're just going to go through and fill out A with the remaining data in first. And you can see that 63, we put the data into the next position. 64, we increment both the first index and J. And so we just sort of fill out AJ. In 67, we're going to do the same thing with second. We're just going to fill out the remainder of AJ with what was in second. Now, we should never have it be the case that both the loop in 61 and 67 get run. Only one of those two loops is going to end up getting run because of the condition we have in line 44. 44 says that first is less than first dot length and I second is less than second dot length. So what we know when we're done with the loop in line 44 is that one of those conditions is not true. Either I first is not less than first dot length or I second is not less than second dot length. One of those is not true. And since 61 and 67 is checking each of those smaller components, we know one of them is not going to get run. 61 or 67 will not get run. That's fine. That's just part of the logic of the algorithm. We don't need them both to be run because in 44, one of the arrays got exhausted. And so the one that did not get exhausted will get covered in 61 and 67. We'll end up moving all of our data into AJ. AJ is a reference, and so when we are done with this method, we will return from merge, having put all of the data from first and all of the data from second into A. We will then return from merge, and A will now be sorted, and we'll be done. Kind of amazing. To demo this, we just wrap it in the main function in a demo class. Start with the main method. We take a particular array that we're interested in creating. We create 20 values here. We fill it with data up to, Fill it with data up to the value of 100. We print out what we start with on line 12. On line 14, we kick off the recursive call. It gets sorted. It's sorted in place, so A comes back sorted. Line 16, we print out the sorted result, and without much fanfare, we see that the program runs in this way. This is a particular filling of our array with random numbers. When you run it yourself, you'll end up getting different random numbers. And then the sorted array is the second one that gets printed out, and we'll kind of look for a few elements to make sure they copied over. So 8 goes from there to there, that looks good, and 81 goes from there to there, that looks good. You can see we've got a double here, and it handled that fine. Up here was our first 76, and here was our second 76. So just a few sanity checks to make sure that everything went okay. Merge sort. All right, so let's talk about what the running time of merge sort is in the same way. Let's see if we can analyze this. Now, the analysis of merge sort requires us to do the same kind of work that we did before in calculating how many times each element of the array is visited. We need to do some little mathematical tricks, though, in order to figure out our running time. So we have an array of size n. That's the same assumption we made in selection sort. And what we want to do is we want to count how many times each array element is visited. And so that this math works out cleanly, and just to demonstrate what's happening, we're going to assume that the size of n is a power of 2. So it's going to be 2 to some power m. What does that mean? That means that we're going to start with an array that's 32 long, because 32 is 2 to the 5th. Or we're going to start with an array that's 64 long, which is 2 to the 6th. Or we'll start with an array that's 1024. N is 1024. That's 2 to the 10th. I could go on and on. We're just going to make that assumption because it makes our math work out cleanly here in a sec. So to calculate the number of visits we need in order to create the smaller subarrays, first and second, and then to merge the two sorted arrays when we get back from our recursive call, we know that we need to make 3 visits We're going to start with the second part. Let's start with merging. We need to make 3 visits for each element that we want to merge. 3 visits. So what does that mean? We have to look at where I first is pointing. We have to look at where I second is pointing. Look at those 2 data elements. Whichever one is smaller, we have to move to AJ. So that's 3 looks. I first, I second, and AJ. 1, 2, 3. So 3 looks. So to put 1 element in our array takes 3 looks. Our array is n long, so to put n elements in our array takes 3 times n looks. That's the merge portion. So that's where our first bullet point comes from. Our merging takes 3n visits. Let's go back to the first half of the algorithm. We would like to figure out how much time does it take to create our smaller arrays, first and second. What does that take? Well, in order to fill first, in order to fill second, we have to look at 2 different positions in arrays. All right, so first of all, we have to look at when we're splitting our array in the beginning, before we've sorted it, we have to go through each element in our unsorted array. So that's going to be 1 visit to A before it's sorted. Then we have to put the first half into first, that's a second chunk, and then the second half into second. A total of n visits to A, and then a total of n over 2 to first, and n over 2 to second. So n visits, that's 1 set of n, and then 2 halves, that's a second set of n's. So to split our array in the beginning in order to do our recursive calls took 2n visits, 1 to A, and then 1 to whichever subhalf we're going to put A in. Splitting takes 2n, and then merging takes 5n. So our recursive call is going to take 5n visits, but we're not quite complete with this yet. What we want to know then is we want to know the total number of visits to sort an array of n elements then. All right. So let's break this down. If we say that the time it takes to run merge sort is the function t over n, we know that splitting our array into 2 smaller pieces, running our recursive call, and then merging it back together takes 5n. So that's the component over here at the right, 5n. The work that we do in one particular call of sort is to split and to merge. But we also have 2 method calls we make. We sort the first half and we sort the second half. All right, so our overall cost is t to the n. That's the function that we're going to define. We know it takes 5n worth of work in the sort method, and then we make 2 recursive calls on half the size of our array. So we have t over n plus 2 plus t over n plus 2, however much time that our recursive call takes, plus the 5n that it takes to split and merge. So we can represent t over n as 2 times t n over 2 plus 5n. That's how much time it's going to take. An array of 100 elements is going to take amount of time proportional to 5 times n and 2 times n over 2. But this is recursive, so we haven't answered exactly how long that is. We've just defined it in terms of itself. All right, so let's replace this n with n over 2 and see what we end up getting as a result. We're just using this formula here, but instead of plugging in n, we're going to plug in n over 2. So what is t of n over 2? Well, we're just going to take n over 2 and plug that in everywhere we have n up here. So n over 2 divided by 2 becomes n over 4, and 5 times n over 2 becomes 5 times n becomes 5 over n times 2. So all we've done here is a real simple textual substitution. We've taken this formula, and instead of using n, we've plugged in n over 2. So this is really like algebra, basic algebra. You just have to sort of understand what's happening. Now what we're going to do is we're going to combine this. We now have a definition of what t of n over 2 is, and so we can go back up here and we can rewrite t of n in terms of what we just figured out is the formula for t of n over 2. And so we end up getting that t of n is 2 from here times t of n over 2. Well, what is t of n over 2? It's right here. So we'll plug that in. it's 2 times t of n over 4 plus 5 times n plus 5 times n, because the 2 right here distributed across to our 5 over n over 2. So we got that right here. When we have this 2, that is where we get 2 times 2 n over 4 right here. And then this 2 also multiplies across 5 n over 2, making that be 5n. And then from our original definition, we have our 5n left over, so we have another 5n there. So now we have t of n can be represented in terms of t of n over 4. Well, so we've pushed our definition of t over n down to a smaller number, which is good, but we still don't know what t of n over 4 is. Well, we can do the same textual substitution that we just did here as well. So we say now we're going to take the formula that we got for t of n and we're going to plug in t of n over 4. And that ends up being 2t of n over 8 plus 5n over 4. Now we have this function here. We have a definition of t of n over 4, and we can plug in t of n over 4. And we see that we end up now, when we simplify terms, that t of n ends up being 2 times 2 times 2 times t of n over 8 plus 5n plus 5n plus 5n. So now we start to see a pattern of what's happening as we split the size of our problem in half and in half and in half. And we can collect these 2's and we can collect these 5 over n's, and we can rewrite the formula in terms of these splittings in half. So what we can do is we can say that t over n is equal to some power of 2 to the k, that's all the 2's from the beginning, times however many times we're splitting t in half. So it started with t divided by 2, then t divided by 4, and then t divided by 8, plus however many 5n's represent the number of times we've split together. So now here comes the mathematical tour de force, I guess. We assume that n is a power of 2. And we just introduced the variable m to say what that is, 2 to the m. So if k equals m, the number of times we've split it, then we can say that t to the n is 2 to the m, t n divided by 2 to the m, just doing a textual substitution here, plus 5 times nm. T to the n, therefore, can be rewritten as n times a constant, t to the 1, plus 5nm, which we can then rewrite tn as being n plus 5n log base 2 of n. Well, where does this log base 2 of n come from? Well, we're solving for m. So if we take this formula and we solve for m, take the log base 2 of both sides, m equals log base 2 of n. So here's log base 2 of n. So we end up that the running time of merge sort is this formula, n plus 5n log base 2 of n. Using our order notation, what we care about here is we care about which is the highest order term in this function. This second term grows on the order of n times something else, log base 2 of n. So this is growing fast, but not as fast as n. This is growing as n. So this whole term is growing faster than this term. And so we can disregard this term here and say that this algorithm is order n log n. So we drop our lower order n, we drop our constant factor, we drop the base of the logarithm because all logarithms are related to each other by a constant factor. We can change the base of a logarithm by multiplying times a constant factor. And so we're left with a big O notation that merge sort in terms of the number of visits is O n log n. Merge sort grows not as n squared, but as something smaller, n log n. Selection sort is n squared. Merge sort is order n log n. This function grows much, much more slowly than n squared. And if you graph them out, it grows so much more slowly, you almost can't see the growth in merge sort compared to selection sort. So you can run this algorithm. You can use collection sort if you want and compare it to selection sort, and you can get real numbers here. And you can see that at 60,000 elements, you'll get something like 19,000 milliseconds to run selection sort. That's 19 seconds. You're sorting 60,000 elements. That's like not very many. That's far less than the number of alumni at Westmont, right? And that's going to take 19 seconds. Imagine if you were trying to sort social security numbers or license plate numbers or DNA sequences or anything that has a significant size to it. 19 seconds. Merge sort doesn't even take 1 second. Significantly faster. And why? Why is it faster? Because we had a better algorithm. Like, it's not about the computer speed. None of this mathematical analysis has anything to do with the computer you're running on. None of it has anything to do with your operating system. None of it has anything to do with the speed of your hard drive or how fast you type or whether you have a big screen or a small screen. It doesn't have to do with whether you used renewable resources or fossil fuels. It has 100% nothing else to do with anything except the algorithm that you're choosing. The way in which you're moving numbers around is the difference between waiting forever and maybe not completing a sort and completing it almost instantaneously. This is amazing to me. It is amazing that data moved in different ways can accomplish the same work with enormously faster consequences. And this is like the kind of thing that is deeply exciting to me about computer science, is that a clever algorithm, things done more intelligently, can make the world sort of a phenomenally faster and better place, and you never see it. Never see it. It's in your computer somewhere. It's an idea. What's an algorithm? It's like a story. It doesn't even exist in the physical world. It's a pattern. It's a mathematical story that we tell through code. It's just amazing. So with that said, I think we're kind of done for everything I want to cover in lecture for chapter 14. If you're in the textbook, you'll notice that there's another version of merge sort called quicksort. Quicksort is a little bit faster than merge sort because it doesn't require another array. It doesn't require, it's not faster in the sense of like n squared to n log n, but it's faster in terms of just not needing as much memory. So in practice, oftentimes quicksort is used rather than merge sort, but merge sort is a little bit easier to teach. Okay, so I'm going to wrap up here unless there are any questions, and there's going to be two follow-up short assignments to do today that I will release in a second. I just wanted to make sure we were able to cover the material before I release them. I think it should take you maybe 15 minutes or something. Chance to review what we talked about, maybe take a look at the textbook. All right, with that said, let me just check to see if there are any questions in game. Is merge sort the best? Okay, so the question, let me just do YouTube. The question is merge sort the best known algorithm? I would say quicksort is the best known algorithm for the general problem of sorting an array whose contents you don't know anything about. If you know something about the contents of the array that you're sorting, any kind of constraint on it, maybe what the highest number is, or if it's sorted at all, you can do better than quicksort if you have knowledge about what's in the unsorted array. But for the general case where you have an array and you don't know anything about the way that array is ordered, all you have is a compare to function, quicksort is the best known algorithm. Okay, one other caveat. It has to be larger than like 10 elements. If it's larger than 10 elements and you don't have any constraints on the array, then it's the best known algorithm. So if you're asked at a dinner party, quicksort's the fastest. If you're asked at a computer science interview, caveats. Good question, though. All right, great. Thank you for your attention. You're dismissed. Computer science is awesome.
Thank you, Professor Patterson.
You're welcome.
Thank you, Professor Patterson.
You're welcome. All right, I'm going to stay in game for a sec, but I'm going to shut down our YouTube broadcast. All right, so for the sake of YouTube, it is April 19th, Monday. We're covering sorting and searching. Had good coffee. Very excited about computer science. Signing off.